RoboSub has evolved a great deal over 20 years, but one thing has remained constant: the submarines need to be autonomous as they tackle the course.
That means the students need to do more than just design a capable mechanical and electrical platform. They also need to program the vehicle to demonstrate those capabilities without receiving any human assistance along the way.
20 years ago, as far as autonomy goes, it was basically a PID loop. And autonomy has progressed such that there are teams now that they don't even know what the sub is going to do.
A major component of autonomy is perception, having the robot know what to look for under the water. Recent technological advances in deep learning have changed the way some teams approach that problem, allowing them to train their sub's visual systems using video data from previous missions.
In addition to changing the way vision systems are tuned, machine learning perception can affect the higher level autonomy system by making it easier for the robots to approach tasks in the order that they're encountered instead of following a preset mission plan.
Our team does not have a very large number of programmers, so for us a machine learning approach is groundbreaking and improving our capabilities and what we can do. Labeling is still pretty intensive, it requires a lot of people, but it doesn't require the applied work that programming and handcrafting algorithms did before machine learning.
Because our vision processing software isn't looking for just one thing in particular, it's searching for everything all the time, our AI can switch between doing different tasks depending on what it sees, and we're also able to take that and feed it into our localization engine to get a better idea of where we are.
Of course, increased autonomy makes it even more important that the robots be able to assess whether they've succeeded or failed at a task, and know when it's time to move on.
Based on our position, we could roughly estimate where XY coordinates we are in the pool and say, are we closer to the torpedoes or are we closer to the octagon? And so the way we determine the success is whether or not you actually end up firing the markers. For example, for the markers, you have to find a rectangle that has another rectangle around it. You have to line up perfectly and then drop it in. We can't actually see the marker going in because it's black going into a black hole, but we're usually reasonably confident that that's a success.
Machine learning approaches are also having a positive effect on the spirit of the competition, as teams now have an additional way to collaborate with one another by sharing their training data.
It's all open source for us, including our training data, and so lots of other teams have been using that data and trying to either emulate what we've been doing or trying to create their own algorithms.
We used old data from 2 years ago, and that was completely different water condition and completely even different settings, but it was not as promising as this year. We got a lot of new footages. We're recording every time we do our test, so we just basically share the footages around teams.
The requirements for autonomy have steadily increased over the years, with more complex tasks, more decision points, and fewer explicit path markers between tasks.
Teams are increasingly turning to simulation environments as a means of testing autonomy behaviors without the extra work of requiring the physical submarine in the water.
The simulator's been pretty useful. We could generate sensor data for IMUs, DVLs, even computer vision, and this allowed us to test our motion planning.
Our simulator has come a long way in the last year. Now most of our models are empirically trained versus before they were sort of imagined. But when they're empirically trained, you get a much better estimate of what the vehicle is going to do and how your algorithms are going to work.
As some teams begin to experiment with multiple vehicle approaches, we can expect to see the autonomy behaviors become more sophisticated and eventually require explicit coordination and communication between the robots.
This year, our mini-sub is able to run half of the course, but doing the non-hydrophones tracking-based tasks, while the main sub is able to focus on the higher value, higher risk, higher reward tasks.
Another project we're trying to get working was the acoustic communication between both subs and be able to work together to complete the tasks. So not only can they react to whether or not they were able to succeed or fail on a certain mission, they can react to how the other sub did on a specific mission.
It's an exciting time to be involved in autonomous systems engineering, and these students are getting a great introduction to the challenges of real-life autonomy.
20 years of RoboSub have demonstrated that the field continues to accelerate rapidly. We'll be here to keep you up to date with all the trends in autonomy at RoboNation.org.